Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on definite integrals. So I want students to be able to evaluate definite integrals. That means we're going to have an integral and we're going to give it a value. You're going to come up with an answer that's just one number. So let's return to this problem here, which we saw in a previous video. So I want to find the area under the curve y equals x squared between x equals 1 and x equals 5. I want to find this area here in yellow. So previously, we looked at drawing rectangles under this curve. You know, I could draw a couple of left rectangles like this, and they often didn't give a great approximation of the area under the curve. So that's if I draw 3 rectangles. What about if I draw a few more? So now I've drawn a few more. I've drawn 6 rectangles under the curve and it gives me a better approximation. So hopefully you can see the more rectangles I draw under this curve, the better my approximation will be. So I want to draw heaps and heaps of rectangles. It would be great if I could actually draw infinitely many rectangles. The problem with doing that is, you know, if I have to find the area this, the area this, the area this, it's a tedious and long process. But fortunately, there's one really amazing fact that we're going to utilize. You see, as you add more and more rectangles, the sum of the area of these rectangles converges to an antiderivative. So the area can actually be given by the antiderivative or the integral of x squared. So how will that end up giving us a number? Well, what we want to do is we want to find basically the change in the antiderivative between our two values, x equals 1 and x equals 5. So we write that here, x equals 1, x equals 5. So we haven't done this before, done an integral where there are 2 numbers here. This makes it a definite integral, having the numbers here. And when you do a definite integral, your answer is just one number. So how do we actually go about calculating this? Well, we know that the integral means the antiderivative. So the antiderivative of x squared we know is x cubed on 3 plus some constant. And what we want to do is we want to find the change, the difference in the antiderivative from here to here. So we're finding the value of the antiderivative at this endpoint and subtracting the value of the antiderivative at this point. So usually we put up a line here and say we're evaluating it between x equals 1 and x equals 5. So all I'm going to do is substitute in this point into the antiderivative and then this point and then subtract them. So if I substitute in x equals 5, I just get 5 cubed over 3 plus c. So that, this in brackets is what I get when I substitute x equals 5. Now I'm going to substitute x equals 1 into this antiderivative. I'm just going to change x to 1. So that will become 1 cubed over 3 plus c. So now, let's go through and simplify this here. So we have 5 cubed on 3 minus 1 cubed on 3. So that actually gives us 124 over 3, which is 41.3 recurring. But we have the c's here. C minus c is, of course, just 0. The 2 c's here cancel each other out. It is for that reason that when we do definite integrals, we don't need to worry about the constant of integration because they always cancel out like that. So we're just left with 124 over 3, which is 41.33. The 3's go on forever. And it's units squared. That is the area under this curve between x equals 1 and x equals 5. So rather than drawing heaps and heaps of rectangles, because you know we need to keep drawing more and more to be more accurate, rather than drawing heaps of rectangles, we can find the area under a curve by just evaluating the definite integral. So that is the antiderivative evaluated between the two endpoints. So let's look at one more example. So let's find the area under this curve here between x equals pi on 2 and x equals pi. Now, if you like, you could put this on your graphics calculator, but the point is I don't even need to graph this in order to find the area under the curve. I don't need to draw any rectangles or whatever. All I need to do is find the definite integral. So I'm looking for the integral of 4x cubed minus sine x, and you'll often see a dx there to indicate we're integrating with respect to x. So then normally instead of writing x equals, we just write lower value and higher value. So always put the higher value up here and the lower value down there. So these are the two x values. So all we do is integrate, find the antiderivative. So the antiderivative of 4x cubed, so this is a power function, increase the power by 1, divide by the new power, so it's just x to the power of 4. So now we integrate minus sine x. Remember, if you differentiate cos x, you get minus sine x. So what goes here would be cos x. So if I differentiate this, I get this. So now we're going to evaluate this between x equals pi on 2 and x equals pi. Remember, we don't add any c's, no plus constant of integration, because they would cancel out anyway. So we're going to substitute x equals pi into this function here. So we would just get pi to the power of 4 plus, now cos of pi is minus 1. And then we're going to subtract when x is pi on 2. So x to the power of 4 plus cos of pi on 2, which is 0. So you can just put that on your calculator and you get about 4.73 units squared. Again, we found the area under the curve between these two values without even needing to graph it. So remember, area under the curve is the definite integral. The definite integral is similar to the integrals you've been doing, except it has two x values and no constant of integration. To evaluate a definite integral means you give an answer that's just one number. You evaluate the antiderivative at the higher x value, evaluate the antiderivative at the lower x value, and subtract. How easy is that? All right, thanks so much for tuning in. This has been the luckiest maths teacher in the world. Have a great day.